Now we introduce the matrix inverse. So let's say we have two square matrices A and B. If A times B is equal to B times A is equal to the identity matrix, then we say that B is equal to the inverse of A. So in general, A times A inverse is equal to A inverse times A is equal to the identity matrix. The reason you call the inverse A to the power of minus 1 is because it's just similar for numbers. For example, if I have the number 5, the inverse of 5 would be 1 over 5. So 5 times 1/5 is equal to 1. So 1/5 is the same as 5 to the power of minus 1, and that gives you 1. So for multiplying numbers together, 1 is like the identity. So, if I have any number, A times 1 is equal to 1 times A is equal to A, no matter what A is. Same for a matrix. A times the identity matrix is equal to the identity matrix times A is equal to A itself. So the inverse of a number like 5 is a number that you multiply it to get 1, where 1 is the number that you multiply by a number to get itself back. So the inverse of a matrix, the inverse matrix, is the one that you multiply by A to get the identity matrix. So can we calculate an inverse for any matrix? Well, it must be square first of all, and most importantly, the determinant of A must not be equal to 0. So if the determinant of A is 0, there is no inverse. Or we can say that the inverse A to the minus 1 does not exist. So here's that definition in the notes. Given a square matrix A, if we can construct a square matrix B such that B times A equals A times B equals the identity matrix, then we call B the inverse of A and denote it by A to the minus 1. And there is a nice formula to calculate the inverse of a 2 by 2 matrix. So if A is equal to ABCD, then the inverse is found by taking 1 over the determinant of A times this matrix, D minus B minus C A. So you see you've swapped the A and the D, and you've said minus B and minus C. So notice that in front of this formula we have 1 over the determinant. If the determinant was 0, then 1 over the determinant does not exist, or not defined, because it's equal to 1 over 0. So this formula only applies if the determinant is not 0. If it's 0, there is no inverse, and the formula doesn't work. So here's an example applying the formula and getting the inverse of this matrix to be this one. So if we just check that, let's put that inverse down and multiply it by that first matrix. So we get minus 2 times 1 plus 1 times 3 in the top left. We get minus 2 times 2 plus 4 up here. We get 3 over 2 minus 3 over 2 down here, and we get 3 over 2 times 2 minus 4 over 2 down here. And if we multiply that out, that's minus 2 plus 3 is 1, minus 4 plus 4 is 0, 0, and that's 6 over 2 minus 4 over 2 is 2 over 2 is 1. So that worked. We multiplied a matrix by its inverse and we got the identity matrix back, as you should. The formula for a 3 by 3 matrix is a bit more complicated. So it's given here, and what we say is that the inverse of A, if A is 3 by 3, is 1 over the determinant times the adjoint matrix. of A. So the formula for that is given here. So it is the matrix of cofactors transposed. So I'll just go through that. So let's take A11, the cofactor of the first row and first column. So to calculate that cofactor, remember your table of signs. So you put the appropriate sign times the appropriate minor. So for A11, or big A11 is the cofactor, small a11 is the element in the matrix A. To get the minor, I delete that row and column and I look at the determinant of what's left. So that's how I got this one. Let's try another one. Let's try A23. So the appropriate sign is a minus, so that goes here, and the appropriate minor we get by going to element 2, 3 here, deleting the row and column, and taking the determinant of what's left. So the minor there is A11, 1, 2, 3, 1, and 3, 2. So that goes in here. So you do that for all of them. So it's a bit of work to calculate the inverse of a 3 by 3 matrix this way. Just take it one step at a time. Get the determinant, get the adjoint matrix, one element at a time, put them together, get the transpose, and then you have the adjoint matrix divided by the determinant, and that's your inverse. Have a go at some of the exercises here, and I'll put up some examples soon.